Greetings and welcome once again to my new calculus channel. Today I'm going to be discussing the kinds of terminology one finds in mathematics, mainstream mathematics, and why it leads to so many not being able to do mathematics. Namely, it's either ill-formed, inappropriate, or just simply wrong. So let's begin. Now, humans communicate using language, don't they? And even the symbols that they use have a meaning that is expressive of the words of a human language. So it behooves us to call objects using appropriate names. Okay, we shouldn't use a name that doesn't describe the object or the concept ever, because that causes confusion. So there are many malformed names and terminology in mathematics. And why is this so important? It's important because when we try to teach mathematics, our success depends on using well-formed concepts. And it's a shame that when you ask most people whether they like math or not, they'll tell you they don't like math because they don't understand it. And for good reason. There are so many ill-formed concepts and malformed names. So the reason that we should strive to use appropriate names is obvious, but apparently not in the case of mainstream PhDs who make absurd claims such as this. The use of symbols is clearer and avoids the mistakes in natural language. Well, I can't imagine anything more stupid than that. Okay, so one might turn around and say, well, the audible words are also symbols. That's sort of that's not entirely true, because the words that we use acquire a meaning, an initial meaning and an evolution in meaning. Okay, so it's not at all the same as taking a mathematical symbol and saying it's more valid to use that, or it's safer to use that than natural language. So let's take the first example. The Wikipedia says that in mathematics, a variable, from the Latin variabilis, or changeable, is a symbol and placeholder for a quantity that may change, or any mathematical object. So I'm not going to waste time on that garbage, but note that those who run Wikipedia are mainstream mathematics academics. And so why is the above statement so wrong? Let's see. First of all, quantities never change. For example, x plus 3 equals 5 does not mean that x may change or ever changes. In fact, x is a constant in this equation, which is exactly the opposite of variable. So why do mainstream academics call x a variable and define it as something that, as you see up here, that may change? That's rubbish. It never changes, ever. Okay? So what about f of x is equal to x plus 3? Does x or f of x ever vary? The answer is very simple. Every pair x f of x never changes, because then the straight line described by f would not be the same straight line. The x's on the x-coordinate line and the corresponding f of x have been constant since past perpetuity and continue to be constant indefinitely. Nothing has or will ever change. Okay? So the best way to describe x would be to call x a placeholder or a symbolic magnitude or number. Variable is decidedly wrong. Okay, let's look at one more definition. In math, a variable is a letter used in place of an unknown number in equations, expressions, and formulas. Well, the above definition is also wrong, because in most cases, the symbolic number is known or can be determined. Whether x is known or not is irrelevant, because if x indeed exists, then x most certainly is not changing. Okay? And if there's more than one solution to x, those solutions are not variables. They're constant. It's true whether one finds value in a quadratic equation or in a system of equations or what have you. Now, how about expressions such as the one that you see over here, 4 less than or equal to 5 or x less than or equal to 5, are these valid? So while it makes sense to write x is less than or equal to 5, because you don't know what is x right now, it is nonsense to write 4 is less than or equal to 5, because this is an invalid logical disjunction. Okay, so let's explain that. To write 4 is less than or equal to 5 means 4 is less than 5 or 4 is equal to 5. Well, this second conditional here is impossible. Okay, and I'm not saying that the or means both this condition and this condition. It doesn't. It means either of them or both. Okay, but in this particular case here, it cannot. The second condition, it's invalid because 4 can never equal to 5. Okay, so for any logical disjunction to be valid, both conditions must be possible, right? It doesn't mean that they must both occur, only that they must be possible. And this can only happen if you use a placeholder such as x. For example, if you say x is less than or equal to 5, right? That's fine to use. So this logical disjunction does not mean 4 is less than 5 and 4 is equal to 5. Rather, it means that in any such expression, either condition is possible. So to write 4 is less than 5 or 4 is equal to 5 is an invalid logical disjunction because 4 can never equal to 5, meaning that the or part is invalid. This or part here is invalid. So the disjunction x is less than or equal to 5 is valid until x is replaced by an actual number or magnitude, in which case only one of the comparison operators is possible and the other is not. Okay? In computer science, these operators are evaluated from a different perspective, which is not the same as in mathematics. So for example, the conditional expression x is less than 5 or x is equal to 5 will return either true or false, depending on the value of x. It will return false only if x is greater than 5, and in any other case, it will return true. So it would not make sense to write code as follows. If 4 is less than 5 or 4 equals to 5, then execute the routine. Because in this case, most well-written compilers would only evaluate the first condition, this condition, right? That is, 4 is less than 5. However, if one wrote 4 is equal to 5 or 4 is less than 5, then a compiler would evaluate both, thus wasting time on this first condition, 4 is equal to 5. And in mathematics, such practice makes no sense, okay? Now, in a language such as C or C++ or Java, etc., you might find the following code. If x is less than 5, double vertical bar, x is equal to 5, then do something. This here means if x is less than 5 or x is equal to 5. So it's a symbol called a logical connective, and in natural language it means or. Note, in natural language it means or. Just imagine if somebody had to write that without explaining to you what it means in natural language. You'd have no clue what this means. So anyone who says that symbols are better than natural language is quite frankly an idiot. For those who still insist that symbols are sufficient, I can only suggest a visit to your psychiatrist as soon as possible. Now, Wittgenstein was one of the prime idiots behind this very flawed idea that concepts in mathematics can only be perfectly described using symbols. So in a sense, the spoken word is also a symbol which has acquired a meaning that people understand. But such meanings are usually to be found in the popular dictionaries, which are things that mainstream mathematics academics appear to hate. No surprise in that their theories are replete with so many ill-formed concepts and terminology that makes it not only difficult to understand, but also impossible in certain instances. They decry infinity on the one hand, and then on the other, they talk about many levels of infinity, according to their leader, George Cantor, who is the father of all mainstream mathematical cranks. Now, one can argue with the baboons ad infinitum over what the meaning of 1/3 is equal to 0.333 ... And all it means is that this here is shorthand for the series, 3 tenths plus 3 hundredths plus 3 thousandths. But they can argue about this ad infinitum. So much for their preference of symbols over natural language. Okay, is it any wonder that so many people think they are bad at mathematics? Now, don't get me started on calculus, because then I could write a set of encyclopedias and not just a simple little article like this based on ill-formed concepts that are used in mainstream mathematics. Well-formed concepts, which has a link here, which I suggest you study, are not a luxury, but a necessity in any science. Okay, they are needed. You can't do without them. If you leave them out, you will not understand what you're doing. Going back to this example here, mainstream academics will tell you many different things. They'll say that it's a limit, that it means 3/10 plus 300 plus 3,000, etc. Others will say, no, it means 1/3. But 1/3 has a very rigorous representation as 1/3. So this here is an attempted measure of 1/3 in base 10, which, by the way, the most important theorem in mathematics, number theorem in mathematics, says cannot be done. So not only are they basically calling a theorem false, but they're showing exactly how ignorant they are of the design and architecture of radix systems. So please try to use well-formed concepts and appropriate terminology when you're talking about mathematics, because it's not a luxury, it's a necessity. If you haven't already subscribed to my channel, please do so. And you can contribute money on my Odyssey site or credits, and I could definitely use that. Spread the news and tell all your friends about my channel, and I'll try to produce another interesting video sometime in the near future. I'm John Gabriel, and this is New Calculus Channel. Till next time, goodbye.